All right, so larger telescopes are going to collect more light. We know that already because of the fact that we've got this light bucket idea. The larger telescopes are going to collect more light. And they also tend to make people happier. Because you can actually see a slight difference in expression here. It's a little bit happier. It's not really a controlled experiment because maybe it just has better data work, but who knows. But I like to think it's actually because it's seeing a brighter image there. And not just a brighter image, but actually a more detailed image. When you go to a larger telescope, you're seeing a brighter and more detailed image. And those two facts are actually connected to each other. The person on the left, looking at this cluster of stars, sees the stars as kind of blobby, kind of spread out, smeared out objects. But with a larger telescope, that same star cluster now looks like a beautiful collection of little glowing jewels. So we're seeing more detail because we're seeing those stars as more sharply defined objects. All right, so the main point of telescopes is the collecting area that they present to the light. Again, the light bucket idea. Well, almost all telescopes are circular telescopes. Hardly anybody bothers making square mirrors. Doing that. So virtually all mirrors are round mirrors. And what it comes down to then is the area of the mirror. So the area is going to be pi times r squared, right? What we're probably going to want to do is compare how much area we have in a couple of different telescopes. So if we suppose that the radius of the second telescope, R2, is twice the size of R1, the area goes as the square of the radius. So R2 is twice R1, then the second telescope over there is actually going to collect 4 times the radiation that telescope 1 is going to collect. It's going to go up with the area. So if we double the size of the telescope, we collect 4 times more light. If we triple it, we collect 9 times more light, etc. Quadruple it, 16 times more light. So we're getting a lot of bang for the buck when we at least double it, the aperture of the telescope. All right, but now, the other issue that I mentioned was the fact that we have the ability to create more detailed images when we go to larger telescopes. This gets into this idea of angular resolution, and that's connected with what we call the sort of bending angle of light as it moves in to the telescope. So the light from a distant source is all perfectly parallel to the axis of the telescope. It's going right down the axis of the telescope in a perfectly parallel way. But the light actually interacts with the telescope itself slightly, and that little bit of interaction with the telescope itself causes these rays to splay out a little bit and become unparalleled. So what that means is when the rays actually reach the mirror down here, because of this little bit of interaction, they're not perfectly parallel anymore. There's a little bit of bending of that angle that's been involved. And remember, if they're not perfectly parallel, you don't focus to a perfect focal point. And if you don't focus to a perfect focal point, you get a straight out image. So this little bit of bending of the direction of the rays is actually going to degrade the focus or the image quality a little bit. So the angle of bending limits the resolution of the telescope. So resolution is the ability to see fine, small detail. And this actually is something that depends on what we call the diameter, which is twice the radius, or we also call that the aperture. That's going to be the quantity that's going to determine how large this angle is. So it's going to turn out that that angle of bending gets smaller the larger we make the telescope. So right there, larger telescopes are better because we get less of this bending angle. Less of that bending means more parallel rays, which means a more perfect focal point. So we're not going to go through the actual details of how this formula is derived or anything like that, but it's pretty simple. And what it's giving you is basically the bending angle. This A is the angle of bending that's occurring, measured in this double operating in arc seconds. So we're getting the answer in arc seconds. And the way we compute it is we take this number here, this small number, 2.5 times 10 minus 5, we multiply by the wavelength that we're using to do the operation in angstroms, and we divide by the diameter or aperture of the mirror, or lens actually, in meters. Okay, so it's set up to work with an observing wavelength in angstroms and a diameter in meters. And then this bending angle here is the best you can do with the telescope. There's other limiting factors, like, for example, having a telescope under Earth's atmosphere. That also plays a role in messing up your ability to focus the image. But even if you put a telescope in space, like the Hubble Space Telescope, it is still subject to this theoretical limit of resolution. This is the best that the single mirror telescope is going to do. So that's the bending angle. Remember, smaller is better, because the less bending, the more parallel, the more precise the focal point. And this angle actually turns out to be the angular size of the smallest features that you can see clearly with the telescope. So here we're just playing with this resolution. The resolution is really 4. We are not able to resolve these two stars very clearly, but as we improve the resolution, in this case by going to a larger telescope, we actually end up with a bending angle that's so small, it's smaller than the angular size of this distance here, so we see these things clearly. So when that angular resolution is larger than the angular separation between these stars, then you don't see them clearly as a separated object, and you get blobbed together like at the top end. So basically, if you want to see an object of a certain angular size, your angular resolution better be a smaller number. Your A has to be smaller than that angular size that you're interested in, or it's not going to work out. It's going to be a smeared image at the scale that you're interested in. Okay, so here's the formula again, and here's just a couple of examples worth out. If we're looking at a 1 meter telescope, this is actually roughly the size of the Becker telescope, about a meter or so, a little smaller than a meter. Here's the formula. Again, the wavelengths in angstroms, diameter in meters. If we observe a blue light, 4,000 angstroms, the diameter is 1 meter. We pop the numbers in here. Okay, so what we're doing is, we have this prefactor, 2.5 times 10 to the minus 5. We stick in 4,000 for the wavelength. So the number there is 4,000. And then the diameter is 1 meter, so that's just 1 in the denominator there. Just 1. So it's basically what was that at 4,000 times 2.5 times 10 to the minus 5. Now 4,000 is 4 times 10 to the 3, right? Remember this works. We have 4 times 10 to the 3 times this number. Well, the 4 times the 2.5 would give us 10. And the 10 to the 3 times 10 to the minus 5 would give us 10 to the minus 2. So you end up with 10 times 10 to the minus 2. But that's just 10 to the minus 1, or just 0.1. So we get the final result is 0.1 seconds apart. So the Mason telescope, using blue light, has an angular resolution of about a tenth of a second apart, which is really, really good. We don't really achieve that here in Fairfax because there's another issue, which is the blurring that occurs because of the atmosphere being in the way. The atmosphere itself actually messes up our ability to focus a little bit. So I think I'll end here and we'll pick this up again on Tuesday. So hopefully you can